This is for the TCGA gene expression data. We log in to RStudio and clean up our environment. You can also clean your console with the Control L. And we go to our DreamHigh 2025 directory and the gene expression directory and click on the expression data activity. So the first thing we have to do is to put the author's names in quotes, and you can enter your name where participant name is. We save this as another file, and we can get going. We load the data, and we get two objects, a clinical data frame and an expression data frame, and they pop up in the environment tab as well. So here we're getting the dimensions of the new data frame for expression data. We see that it has 18,351 rows and 1,081 columns. We can look at it as well, even though it's large. So the first column is character data that corresponds to gene names, and the remaining columns correspond to patients and their gene expression levels for each of the genes. So to get a numeric matrix, we need to get rid of the first column, but we want to also make it be the names of the rows of our new matrix. We also want to check that the order of the patients in the columns here is the same as the order of the patients in the clinical data frame. And remember, those appeared in the first column of the data frame. So we check that, whether the column names for the expression data set are the same as the first column in the clinical data set. And that's true, so we don't need to worry about this anymore. All right, so here's where we create our numerical matrix. We remove the first column from the expression data frame because that's gene symbols. And then we set those gene symbols as the row names of our new matrix. And then we'll check it. And that looks good. We have row names and column names and numeric values. So we can calculate the average expression for a given gene either by enumerating the row number or pulling out the row by the row name. And we get the same value for this T-span 6 gene, 996. We can do that for other genes as well, but we'll use the apply function to apply a function like mean to all of the rows. So in the second argument, it could be 1 or 2, and 1 refers to rows. So we're applying to our matrix mean to all rows. And we're going to save that to a new object, mean.expression. And the first 25 values, we get 996, average expression for T-span 6 again. So we can plot this array of average expression values with the histogram. And we see that there are very few genes with high average expression. Let's look into this in a little more detail. We'll create a new object, .high, for only those genes with the average expression greater than 10,000. And we'll see how many of those cases there are. So there's only 201 cases where we have average expression greater than 10,000. So we can zoom in on that. We can create a .low variable by looking at the genes that have average expression less than 10,000 and then making a histogram for that as well. So now we see, most of the genes in our data set have an average expression of less than 2,000. So now we're going to take the log base 2 transformation of our matrix to sort of compress the values of expression in this matrix because they're very small, very large. One thing to notice about taking the log of 0, so here we're taking the log base 2, that's the second argument of the number 0. we get an infinity value. But if we take the log base 2 of 1, we get a 0. So what we're going to do is, since the log of 1 is 0, we're going to add a 1 to every of the values in our matrix. So add 1 to every cell. And then we take the log 2 so we can avoid any cases where there could be an infinity. And we're going to call it a new object.log to remind us that this is log transformed. So for t-span 6, instead of the expression being 996, the log 2 of that is 7.56. So you can apply mean to this new um, expression matrix to get a sense of what those values look like. So we have a very large matrix now, log transform gene expression values for 18,351 genes and 1,082 patients. To do our analysis, we need to take a subset of this data, and we're going to use a strategy that's typically considered. So for genes, we're going to take those that have the highest variance, and that means that the expression values for a given gene have a very large spread across the patients. And we can use the apply function again on our log transform matrix. Now, we're not going to calculate the mean, rather we're going to calculate the variance for every gene. And we'll take a look at that histogram. So interesting, we see that we have variance greater than 5 for, probably the number of genes we might be looking for. So let's consider this. If we pick 5 as our cutoff for variance, we don't want to lose things that are important, like the estrogen receptor gene. So let's find out what its variance is. Okay, so it has a variance of 10. So it'll appear here, and it would be in our list of high variance genes. So how many of our genes will have a variance greater than 5? That's 690. So that's a lot smaller than 18,000, but it's a good start for us with our exploratory data analysis. We'll use the function order to order the variance files, the variance values from high to low, and put that array of numbers, that sequence of numbers, in order.var. Then if we pick 690 as the number of genes we want to consider, we'll create a new matrix. Now it's the log transformed matrix with the 690 largest variance genes by calling those rows for the genes that have the highest variance. All right. Now we can examine that using the dim function. We have 690 genes, 1,082 patients. And we see we start with different genes in our list. These are ones that have higher variance across the patients, and these are their log transformed values. Okay, so you can take some time to go through the box plot code chunks. We're going to continue whittling down our matrix by taking a subset of patient samples. And there's no special strategy for that. We're going to create a sequence of numbers from 1 to the number of columns of our matrix, which is 1,082, and take every fourth sample. So we'll see how many samples that gives us and what proportion of that is. All right, so 271 samples, and that constitutes 25% of our data, which is what we want, right? Because we want 1 out of every 4. So now we finally have the matrix we're going to work with, our matrix. We're taking the matrix that was log transformed, and that we took the highest variance genes, and now we're going to pull out the columns corresponding to our samples. So this is the matrix we're going to work with, and let's check out its dimension information. So it's has 690 rows or genes and 271 patients. So now we can create a heat map as we did for MT-CARS. So we're going to scale our matrix um, as we did with MT-CARS, and then we're going to use the heat map function. And we're going to label the X and Y axes. So this looks very similar to what we got for MT-CARS. We have many more features and observations, so columns and rows. We still see a very nice pattern. So we see a bunch of patients here on the left-hand side that have a distinct shared gene expression profile. So before we continue, let's look at a different color scheme. We'll load in that package. And in this field, people typically use the red-blue coloring scheme. So we'll get the same heat map, just now with values coded from blue to red. And we still see this nice cluster on the left-hand side. So now we want to annotate the heat map. Let's remind ourselves what's in the clinical data frame. We looked at things such as estrogen receptor status. And in annotating our heat map, we want to use the status of the estrogen, progesterone, and HER2 receptors. So we remember from last time that we had negative and positive values for the estrogen receptor. So we're going to first create a new clinical data frame that contains only those rows that correspond to the samples we're actually looking at. And then we'll create a variable X where we just take the estrogen receptor status. So let's take a look at that. All right, so we have positive and negative values. And we can't put positive and negative under the columns of our heat map as too large. So we're going to substitute positive for a plus sign and negative for, we'll just use a period sign. So if we do that, now we have a little table for ER where we have 13 null values or missing values, 57 negative, and 201 positive values. So we can take this new object, ER, and put it in the label for the columns. We're going to label our columns with those plus and dot symbols. So we're creating the same heat map as before, but now we have positive signs for ER positive and dots for ER negative. And interestingly, this cluster on the left corresponds to all ER negative patients.